We can see you. We can't see your screen yet.
Okay,
But I'll already introduce you. So Patryk is speaking to us from the University of Bristol, and he is going to talk about catalysts in quantum thermodynamics. And he'll tell us why all states are universal in this sense.
Thank you, Felix. So, can you see my screen now?
Yes, yes.
Okay, great. Okay, so thank you, Felix, and for introducing me. First of all, I would like to thank all the organizers for allowing me to talk today and giving me this opportunity to share our results. My name is Patryk Lipka-Bartosik, and I'm working in a QIT group at the University of Bristol. And this work I'm going to present it to you today is a joint work with Patryk from Bristol. Okay, so before I'm going into the details, let me just slightly recall a very standard problem, which we all perhaps know very well. So the standard problem studied in classical thermodynamics, where we start with a system which is in a thermal equilibrium with a big heat bath at some inverse temperature beta. And let me suppose that we have some thermodynamic process which changes the system's Hamiltonian such that the system equilibrates toward a different state now. So we know that this transformation can happen if and only if the Helmholtz free energy of the system decreases during the process. And this is one of the instances of the second law of thermodynamics. So this reasoning can be generalized to states which are out of equilibrium. And in that case, the second law now can be written using the so-called non-equilibrium free energy, which essentially generalizes Helmholtz free energy with a term which is just the relative entropy of the system given its respective thermal state. So if the system is initially in a Gibbs state, then this term reduces to zero, and non-equilibrium free energy reduces back to the Helmholtz free energy. Okay, so this situation is a bit more complicated for quantum systems, and in that case, the free energy no longer describes which state transitions are possible and which are not. And in fact, it's replaced by a family of generalized free energies. And more intuitively, this captures the fact that for quantum thermodynamic systems, for quantum thermodynamic transformations, these transformations depend on the whole structure of the energy distribution and not just on the averages. And importantly, in the limit of infinitely many systems and modulo some technicalities, one can prove that all members of this family of quantities essentially reduce to the non-equilibrium free energy. And just a small side note, so these were the quantities which were, I guess, introduced by Nelly on Tuesday, and here this additional term which we have in the definition of the generalized free energy is a Renyi relative entropy, which also quantifies the distance. Can be thought of as quantifying the distance from the state, so from the non-equilibrium state to the equilibrium state. Okay, so unfortunately for general quantum states, these free energies provide only necessary conditions for state transformations. However, when states are block diagonal in the energy eigenbasis, they do provide necessary and sufficient conditions for those transformations. And in that case, we can also slightly simplify this difficult quantity, the alpha, and it can be written just using the eigenvalues of the state of the system and its respective thermal state. So maybe an important point to highlight now is that these results rely on a very specific assumption, in particular that there is some ancillary system, a thermal machine or a catalyst, which is not consumed by the protocol, but nonetheless can make the transformation possible. More specifically, if these second laws are satisfied for a pair of states, then there is another state, omega, which is not consumed by the process, but still enables the transformation. So in other words, without this state, we could not perform this transformation. And this becomes more natural once we realize that standard treatments essentially capture implicitly capture an analogous idea. To, for example, to perform thermodynamic transformations, often one needs to supply additional devices which are generally have to be reused or are used in a cyclic manner. For example, engines, the machinery of a heat pump, or parts of the refrigerator. And in this way, catalysts can be thought of as models of thermal machines or some experimental apparatuses which facilitate or even sometimes completely enable the transformation. And this general phenomenon of lifting restrictions without being consumed is called quantum catalysis. Okay. So hopefully this approach opens up several new problems. And first of all, we know that second laws only guarantee that the catalyst exists. So even if they are satisfied by a pair of states, rho and sigma, it may still be very difficult to find which particular state catalyzes a given transformation. And this intuition comes from macroscopic experience. If we consider chemical reactions, then very often they can be catalyzed only by very appropriately chosen catalysts. And thermal machines very often also need to be carefully tuned before the desired transformation. For example, combustion can happen. And this reasoning leads to two natural questions. So first, how such catalysts should be determined? Is there any general method we can construct to find catalysts which are useful? And the second question is, can catalysts which are useful for one transformation also catalyze other transformations? And in other words, how special are generic catalysts? So up to date, most results in the literature are based on constructing a very finely tuned catalyst. And this leads to a certain folklore knowledge that catalysts are very special quantum states. And in this work, and here, so now we arrive at the main result of our work. So which essentially contradicts this intuition. And in what follows, I will try to convince you that in the research theory of quantum thermodynamics, any non-equilibrium state, as long as we are provided enough copies of this state, can serve as a catalyst for all transformations that are allowed by the second laws. And at this point, I want to also emphasize that the problem of catalysis can be tackled irrespectively of the second law. So it's in fact a more general problem and can be studied independently of the specific theoretical framework. And in this spirit, the methods which we use here can be readily applied to other resource theories, like the resource theory of entanglement or coherence, or other resource theories. And furthermore, most of the arguments I'm going to make now do not rely on the resource theoretic formulation, and this gives at least hope that this universality phenomenon can be even more general. Okay, so with this, let me now move on to presenting our main protocol, which essentially allows to use any multi-copy state as the catalyst for any transformation. So with this, let me denote with omega c an arbitrary, a block diagonal, but otherwise arbitrary state of the catalyst. And remember that our goal is to transform rho into a state sigma without disturbing this catalyst. And the only thing we know about rho and sigma is that they satisfy the second laws. So the protocol consists in 3 steps. So for simplicity, here I use the heat buff. This denotes the heat buff, and I'm just for clarity of presentation, I'm denoting 2 parts of the heat buff, and this is the same heat buff. And the protocol consists of 3 steps. And in the first step, we apply the first unitary, to recall that we have n copies of the catalyst, and when n is sufficiently large, then due to the law of large numbers, the catalyst state almost uniformly occupies its typical subspace, and such a state can be almost in an almost reversible way converted into any other state. And importantly, this conversion can happen with a very small error, which vanishes quickly as number of copies increases. And this is essentially the content of the first result which we use to in our work. So this is a result by Christopher Chuck, Marco Tomamikel, and Kamil Kozekwa. And well, they essentially estimated the error of applying this unitary, which creates some state which we want here. And so for our purposes, we want to convert this multi-copy state of the catalyst into a single copy of a very special state, which we refer to as a dual state. So these are states, it's a family of states which were introduced by Runia Duan in 2005. And essentially, these are very simple states with a classical register and appropriately chosen multi-copy states of the input and output state. So just for a small example, in the case when this parameter k is free, we have the following form of the dual state. And in what follows, I will use the following pictorial representation of the dual state. On the x-axis, I will denote quantum systems, so particles of the catalyst composing the catalyst. And on the y-axis, I will denote the classical register. Okay, so once we properly process the catalyst in the first step, we can now move on to the second step of the protocol, where we apply the actual catalytic transformation. But before I do so, let me present one more result drawn from quantum information theory. And this one is basically a slight generalization of this result by Jensen, and essentially states that given two states which satisfy respective second laws, there's a multi-copy transformation. So there is some k such that k copies of this state can be transformed into k copies of the state sigma. So there's a multi-copy transformation and a unitary which realizes this transformation by acting on the state and on k copies of the state and the heat buff. So as an example, and this is precisely what we will do to construct this unitary V. So as an example, let me consider a situation where k copies of rho are enough to transform it into k copies of sigma. And then if we were to write down the joint state of the system and the catalyst, using this pictorial representation, we can draw the following diagram. And then we can realize that, well, by appending the catalyst and with the system, we can see that we have now a subspace, which we can now convert by applying a conditioned unitary. So this unitary is conditioned on the classical register. And so let's do that. And let's transform it into the following state. Right, and using our V tilde. And after this, we perform a cyclic swap on the classical register so that the first system goes to the second system goes to the first system, and first goes back to the first system. So which essentially gives us the following form. So this can be a cyclic swap, or we can just relabel classical systems without moving physically those particles. And then we essentially do a very similar thing regarding the quantum systems. So we again perform the relabeling, and we finish with the following state. So now, if we were to trace out the system, for example, then so this is the system now, then we will end up with the following state, and this is precisely the dual state which we started from. So this means that the catalyst is retained after the transformation. Moreover, if we were to trace out the catalyst, so we trace out those two particles plus the classical register, then essentially we end up with the state sigma. So this red dot corresponds to a sigma. And this is precisely the state which we wanted to achieve. Okay, so finally, in the last step, we apply the unitary which we used in the first step backwards. And this essentially recovers the initial multi-copy state of the catalyst up to a certain error. So as long as the unitary V doesn't disturb the state of the catalyst too much, then this unitary is able to reverse the action of the first unitary. And by using triangle inequality applied to this transformation, one can easily show that the total error, which is incurred by the catalyst on the catalyst, can be upper bounded by twice times each of those errors applied by each of these unitaries. And this by the first result, which I've shown you from this paper, can be further upper bounded by a sub-exponential term in A, and the number of catalyst particles. And this very quickly approaches zero when the number of particles increases. Okay, so finally, let me combine these three steps into the following theorem. So suppose that we have a pair of states, rho and sigma, which satisfy respective second laws. And then using the protocol I have just described, and using any state as a catalyst, provided it is supplied with sufficiently many copies, we can transform rho into sigma with a very small error on the catalyst. So the error on the catalyst is sub-exponentially small in the number of particles, whereas the system gets transformed from rho to sigma without an error. Well, as long as the heat bucket is infinitely big. Okay, so with this, let me now conclude. And first, I hope I have convinced you that in this resource theoretic formulation of quantum thermodynamics, any state can be used as a catalyst for all transformations which are allowed by the second law. So for all allowed transformations. Furthermore, I want to emphasize that the catalytic protocol, which I have described, is general in the sense that it can be readily applied in other resource theories which are governed by similar second laws, which we refer to as majorization-based quantum resource theories, like entanglement, coherence, or purity resource theory. And finally, and perhaps most importantly, I believe that this gives a hint that this generality here gives a hint that catalysis can be also studied outside of resource theories. For example, models using more realistic assumptions, well, when the control allowed by the experiment that the experimenter has over the system, or the type of interactions that can be created is limited. And this very basic idea of using quantum resources in a catalytic fashion naturally does not depend on the specific theoretical formulation which we use. And furthermore, we now have a couple of interesting results which support this. For example, there is this recent paper which shows that catalysis can be essentially used to enhance one's ability to cool quantum systems, which I highly recommend. And I also believe that it won't be an exaggeration to expect that to see similar catalytic enhancements in the operation of quantum engines. And this is because, well, the working body of an engine, when we use a catalyst, can reach states which would not be accessible without the catalyst. So this gives at least hope that catalysis can boost efficiencies of engines, or just by the same reasoning, perhaps also could be applied in battery charging. Okay, so with this, let me thank you for listening. Thank you one more time for giving me the ability to talk, and I'm happy to answer any questions.
Thank you, Patryk. We have time for a question or two, which if you're a panelist, you can write in the chat, and everyone else you can put in the Q&A or raise your hand, please. Maybe as we wait, if there's until the question comes in. I was curious in what you're presenting. So you're using this pre-processing and this post-processing to convert a arbitrary state into this Duan state, for instance, right?
Right.
And you get this exponentially decreasing error in the number of copies. So this n and alpha, they're both independent of the state in this bottom inequality, or they depend on the state in the end.
Well, so essentially n. So that's a good question. I haven't specified it properly. So so in general, alpha is a parameter which you can choose, and it goes from 0 to 1. And depending on the parameter which you choose, you essentially get a different. So what changes here when you change the system? The system is m. So essentially, n is the number of copies that you have, but then if you want to specify the amount of output copies of your state, so if you were to specify m, then this m is just given by some rate function times n. So essentially, the better state, for example, the more resourceful state you use, or the more energetic state you use, then m can be larger. Yeah, so essentially the relation is here. M determines you how many output states you can produce, and if the state, if your initial state omega is relatively close to a thermal state, then to produce a state which is far from equilibrium needs to have n very large to have a moderate number of copies m.
So any state will do in the asymptotic limit, but you'll need different numbers of copies depending on how resourceful your catalyst is. Is that a way of stating
Yes.
this? Then? Yeah.
Yes.
Cool.
Yes.
Fantastic. I don't see any other questions, and I think it's also time to move on. So thank you very much again, Patryk.
Sorry, can we give a chance to Gabriel to ask a question? Because I think it's the second time when he's raising his hand. I added him, but you're moving on. Gabriel, you're...
Oh, sorry, I can't see this here.
Okay.
I thought this would show up somewhere. Sorry.
Hi, Felix. No problem. Hi, Patryk. Thank you for the very nice talk. I was wondering, could you elaborate a little bit on your thoughts on how this would have potential applications for master equations? I guess I didn't really get that point.
Yeah. So essentially, let me go here. So in general, so in catalysis, the main problem is essentially keeping the catalyst undisturbed, right? So in that case, so by this fact that this method is general, I mean that so we essentially do not base this derivation on the fact that the second laws hold in some sense, or on the specific resource theoretic formulations. So in other words, the only thing which we require is to be able to create this D1 state, so this state here, and to be able to perform a multi-copy transformation. So you can view this protocol perfectly. You could restate this result as the following. So suppose that we know that we can convert n copies of some state into n copies of some other state. So there exists a multi-copy transformation for that case, and it can be realized using arbitrary unitaries like in resource theories, or using a more some fixed type of interaction. But the only relevant thing in this whole protocol is that you can perform this multi-copy transformation using this unitary v tilde. And if your master equation allows for it, so allows to in some sense super activate the state, then basically your transformation can be catalytic, right? And
so, but would it mean, like, for instance, in view of the last talk, that somehow if you have, for instance, a collision model, which in addition to the ancilla BAFs, you also have catalysts, then somehow this could lead to different master equations because of the presence of the catalyst? Would be something in that sense?
Oh, so could you repeat that?
Sorry, so what I meant is, like in view of last talk, which was talking about these collision models and how you can model these discrete collisions with the BAF in a sort of continuous time way to get a master equation, that somehow if you do the same in the presence of catalysts, then this would lead to new master equations which are different.
Yes, so you would essentially, yes, but in that case, so the only way, so here the only place where you use this catalyst is essentially in this step, because all other steps are just relabelings. So the only thing here is that you essentially have this catalyst, and you apply this controlled unitary, which modifies n copies of the catalyst. So I'm not fully sure if if I understand that it would change the master equation. So perhaps, sorry for my ignorance, it's perhaps because I'm not an expert in master equations, but I believe that as long as you are able to perform this multi-copy transformation and in such a way that you don't disturb other parts of the classical register, right? So you don't. So as long as you are able to write down the master equation in such a way that all those classical registers and the corresponding quantum states, they don't change. So if you are able to apply an identity map for them and only apply very selectively your transformation to just one of those classical registers, then essentially I believe that what you do further is just simple relabeling, so you don't apply any dynamics there. So the transformation should be essentially catalytic, at least in principle.
Okay, it makes sense. It seems like a very non-trivial question. Thank you.
Thank you for the question.
Thanks a lot again. I hope I'm not missing anyone else. I don't seem to be able actually, or I'm not seeing any raised hands, I think, on this.
Yeah, we're fine.
If I'm not missing, okay,
No.
fantastic.
Thank you.
In that case, let's thank Patryk again. Let's thank all of the speakers of the session.